Hi everyone, today we are going to talk about partial fractions and how to create them. And we're going to focus just today on linear factors. So this is what the partial fraction decomposition looks like. So if you have some sort of rational expression like this, we're going to today learn how to write it as a sum of partial fractions. So notice that if your denominator can be factored, you have one fraction for each factor. And notice that both of these are linear factors. So those are the types of factors we're going to do today. So we're going to learn how to go about this process. So to do this process, it's a lot easier just to kind of go through a few examples, but there are a few things to look out for. So if you're creating partial fractions, the first thing you need to check is that you need to see if your expression is an improper fraction, meaning the degree of the numerator is bigger than the degree on the denominator. So if it is improper, you're going to use polynomial division to create a mixed number, and then you're going to use the remainder, which will be a fraction, for the following steps. So this is essentially like taking the fraction 3 over 2, which is improper, and writing it as 1 and 1/2 as a mixed number. So then you're going to factor your denominator, and then this is where you start the decomposition process, which, like I said, is just easier to show an example and to go through the steps. However, you do need to watch out for a few things. If you have a repeated factor, such as x plus 1 squared, there's a special process for that. And there's also a special process for quadratic factors, but we're going to cover that in the next video. So let's give this first problem a try. So notice here we're talking about problems with distinct linear factors, meaning all of the factors are linear and there are no repeating factors. So let's first check to make sure that our expression is not improper, and you can see that the degree on top is smaller, so it's not. So we're ready to go. So step 2, we skip straight to step 2, which was to factor the denominator. So we can write it like this: x plus 7 over x minus 3 times x plus 2. So now we're going to start the decomposition of partial fractions. So our goal is to create a sum of 2 fractions, one for our first factor, which was x minus 3, and then one for our second factor, which is x plus 2. But we do have to figure out what those numerators are going to be. So I'm going to call them a and b. So that's what we're going to solve for. So here we have an equation, and it really is a system because there's 2 variables. So now we need to go about solving. So the first thing I'm going to do is multiply both sides of our equation by the LCD. And in this case, our LCD is just x minus 3 times x plus 2. So imagine I multiply every single term by that. If I multiply the left side of the equation by our LCD, the denominator is going to cancel out completely. So we're left with x plus 7. If I multiply this term by x minus 3 times x plus 2, x minus 3 is going to cancel out, but x plus 2 will remain in the numerator. So it becomes a times x plus 2. And then if I multiply this last term by our LCD, the x plus 2 will cancel out, but x minus 3 remains in the numerator. So we have b times x minus 3. So this is going to be kind of our baseline equation. So we're going to take a slightly different approach to solving these types of systems. We're actually going to just start substituting convenient x values and then seeing if it can help us solve for a or b. So by convenient x values, I mean x values that will cancel out full variables. So essentially, we're going to be plugging in numbers that are zeros for our denominator. So imagine if I substitute the value -2, this becomes 0, so that's going to be a convenient number. Or if I substitute the value x equals 3, this becomes 0, so that's another convenient number. So we're going to go through that process. So let's start by substituting x equals -2 into our equation. So we have -2 plus 7, which is 5. And then here we end up with a times -2 plus 2. So you can see that this is going to become 0. So our a term is going to cancel out. And then here we have b times -2 minus 3 is -5. So all we have left is 5 equals -5b. So you can see that we can solve for b. So b is -1. So we've already found one of our variables, but we still need to find a. So we still have another convenient number to substitute. We can substitute x equals 3. So let's go back to our baseline equation, and we're going to substitute x equals 3. So 3 plus 7 is 10. And then we have a times 3 plus 5, 3 plus 2, which is 5. And then you can see for our b term, we have, if we substitute x equals 3, that becomes 0, so our b term disappears. So now we can solve, and we get a equals 2. All right, so now that we have our a and b terms, we're pretty much done. Now we can write our expression as partial fractions. So our a value is 2, and that was 2 over x minus 3 plus negative 1 over x plus 2. So you just have to make sure that you're substituting your a and b values into the correct place, because they're not interchangeable. The 2 has to go with x minus 3, and negative 1 has to go with x plus 2. So once again, they are not interchangeable. But this is our final answer. Okay, so go ahead and pause the video. See if you can replicate that same process and write this. Write the partial fraction decomposition of this expression. Okay, so remember, you factor your denominator. So here's what you should get, and then you could write it as 2 separate fractions, one for each factor. And then you multiply both sides by the LCD, which is 2x plus 1 times x minus 1, and here's what you get. So we have 2 convenient numbers to substitute. We can substitute x equals 1, which will cancel out our a value, so we can solve for b. And we could also substitute x equals negative 1/2, which will cancel out our b value, allowing us to solve for a. So a is equal to negative 3. So here's what you should get as your final answer. Okay, so now we're going to talk about what do we do if we have a repeated factor. So let's take a look at this problem. The first thing to notice is that we actually have an improper fraction here. The degree of our numerator is larger than the degree in our denominator. So we want to rewrite this as a mixed number. So we're going to do a little bit of polynomial long division. So these types of problems, I think they look a little bit scarier than they are. So don't panic. So here we have x, and then x to the 4th plus 2x cubed plus x squared. And remember, we subtract the entire thing. So we're left with 5x squared plus 20x plus 6. And we can't divide anymore, so we're done with our long division. So we can rewrite that expression as x plus, and then we have our remainder, 5x squared plus 20x plus 6 over x cubed plus 2x squared plus x. So we're essentially taking a mixed number like 3 over 2 and rewriting it as, an improper number like 3 over 2 and rewriting it like 1 1/2. So now we can't forget that we have this whole number here, because that's going to be part of our answer. But now we're going to focus on this part to write the partial fractions for our remainder. So then we're going to take that, and we're going to start by factoring the denominator. So we have a GCF of x, and then you could factor that remaining trinomial, and it actually becomes x plus 1 squared. So you can see that we have a repeated factor. They're still all linear factors, but one of them is repeated. So the setup for this type of problem, it looks slightly different. So we're still going to create a fraction for x, but when you have a repeated fraction, you have to create, or a repeated factor, you create one fraction for the singular factor, and then another one for x plus 1 squared. So you kind of work your way up. If this were a triple root, you would have one for x plus 1 squared, and then another one for x plus 1 cubed. So you just kind of follow that same setup. But notice this time, we have 3 variables that we need to solve for. So this one's going to take a little bit longer, but it's not too much harder. So we're going to follow the same process. We're going to multiply by the LCD. And the LCD in this case is x times x plus 1 squared. So the left side of our equation, the denominator clears completely. So when I multiply this first term, the x will cancel out, but we're left with x plus 1 squared. So a times x plus 1 squared. For b, one of the x plus 1's cancel out, but there's still an x, and there's still an x plus 1. And for c, the x plus 1 squared cancel out, but there's still an x. So we have c times x. So this is going to be our baseline equation. And now we're going to start substituting some convenient x values. So you can probably guess that one convenient x value is going to be x equals 0. That's going to be a good one. So let's substitute x equals 0. So on the left side of the equation, we have just 6 equals, so we have a times 0 plus 1 squared, which is just 1, plus b times 0 times 1. So you can see that this will cancel out. And then you have plus c times 0, so this also cancels out. So this one's pretty convenient. You see that we have already solved for a, so a equals 6. So we do have another convenient number that we can substitute. We can substitute for x equals -1, which will clear a couple of our variables. So if we do that on the left side of our equation, we have positive 5, minus 20 plus 6. So then we have a times -1 plus 1 is 0. So you can see that our a term will cancel out. And then we have b times -1 times 0, because -1 plus 1, so our b term cancels out. And then we're left with c times -1. So then here you can see that we have -9 equals -c, so c is going to equal 9. Okay, so at this point we have solved for a and c, but we're still missing our b term, and we don't have any other convenient numbers to plug in. So now, if you look back at our original, or this baseline equation, the last thing we have to solve for, once again, is b. So if we can find a way, we have a, we have c, and then we can pick some other x value, we should be able to solve for b. So at this point, like I said, we're going to substitute what we know a to be. We know a is 6, we know that c is 9, and we're going to pick an x value. You can pick whatever x value you want, but I would pick something nice. So I'm going to pick the x value, x equals 1, just because it seems like the easiest thing to go back and plug into this equation. So let's take a second and do that. So that gives us 5 plus 20 plus 6 equals, so remember, we're substituting for a, so we know that a is 6, so we say 6 times, and then we're plugging in 1 right here. So 1 plus 1 is 2, 2 squared is 4. Okay, b we are still solving for, but we're substituting 1, so we have 1 times 1 plus 1, so it'll be 2. And then we have c, which we know is 9. That was one of our substitutions. And then we substitute x equals 1, so 9 times 1. So now we just have to isolate b. So if we simplify and isolate, we should get -2 equals 2b. So b equals -1. So remember, for that last step, once you have a and c, or any two of your numerators, you can pick a new x value. So just pick a number that you feel comfortable working with. So obviously, if 1 is still an option, that would be a really good one to pick. So now that I have a, b, and c, I can go back and write this as partial fractions. Now remember, this fraction, if you go way back to the very beginning, we do have a whole number portion, which was x. So make sure you write that first. So that needs to be the first part of our answer. So we have x plus, and then we have our a value, which is 6 over x. And then we have our b value, which is -1 over x plus 1. And then we have our c value, which is 9 over x plus 1 squared. So this is our final answer. And I know that this problem, it looks like there's a lot of work and it looks really hard, but if you break it down into the actual math we did, it's nothing that's too bad. But just remember, we had to do some long division. This is how we write with a repeated factor, so make sure you have the setup correct. And then we are going to substitute our convenient numbers, and then we get to pick our own x value once we have solved for 2 of them. All right, this is the last example. See if you can kind of follow that same process, and make sure you are checking for your improper fraction first. Okay, let's check your work. So you do need to do some long division. So when you do that, you end up with x plus 4 over x squared times x plus 1, which you can break up into 3 partial fractions. So remember, x is our repeated factor this time. So we have 1 fraction for x and 1 for x squared, and then a single fraction for x plus 1 because it's distinct. Now we're going to multiply both sides by our LCD, which was x squared times x plus 1, and here's what you get. So don't forget about this x, but we're just focusing on this for now. And then you could see that I substituted x equals 0, which allowed me to find b, substituted x equals -1, which allowed me to solve for c, and then I substituted the b value, the c value, and then I picked the x value, x equals 1, which allowed me to solve for a. And this should be our final answer. So make sure your final answer has that x, because that is part of our partial fraction decomposition. All right, that is all for today. Thank you for watching.